Today, I will talk about the two models of adaptive dynamics of structured populations, analysis, and simulation. These are two works I have recently finished with Louis Almeida, Thomas Lawrence, who is here, and Benoit Patam. Benoit Patam is my postdoc supervisor from the LGL Sorbonne University, and he is my postdoc supervisor. And Louis Almeida is also a senior researcher from the lab. So this is the outline of my talk today. First, I will talk about the Dirac constriction in age-structured models. And then I will talk about the population with the heterogeneous mobility and the proliferation rate. The first project is consider the age-structured models. And this is the work with Louis Almeida and Benoit Patam. And so first, for the age-structured models, I have to say that the age-structured models has been used many times to model various phenomena in evolution biology. In particular, it can be used to show how the evolution affects the cancer incidences with respect to the age. Here is some data. You will see from here that after some age, there will be an exponential growth of the cancer incidences, right? And in fact, in nature, we can observe there are some observations that the cancer mainly affects the individuals beyond the reproductive age. Although most cancers are somatic cancers, there are still 5 or 10% of inherited cancers. For the somatic cancers, it is easy to understand why there is a risk to get the cancers as age increases. This is because as people grow older and older, they will have an accumulation of the mutations. So it is more likely for the normal cells to become the cancer cells. But for the inherited cancers, because they are determined by the gene defects, so and we still observe the similar patterns. So there's one question is that why for the inherited cancers we still have such patterns, and the other question is since the gene defect seems to be bad for humans, so why the natural selection will not eliminate such gene defects? Okay. So now let's maybe the age structure models I will introduce later can give us an explanation. For the age structured models, the motivation is to study the growth process of population structured by age and some traits subject to the aging and the rare mutation, and also possibly the competition. Here we use the A to denote the age of individuals and the X to denote a quantified phenotypical trait. In our case, the X is used to denote the aggressiveness of an inherited disease, and it affects the individuals through the birth rate and the death rate. And here we use the N to denote the population density and the rho to denote the total population at some time. And this is the mathematical model. This is the age structured because here we have the age. And for the first equation, you can see that for the first term, it is for time evolution, and we add an epsilon, small epsilon here to show that we are concerned with the long-term behavior. And the second term is for aging, and the third term is for the death rate. And the last term here, we add this last term to normalize the total population because we are only concerned with the evolution of some trait. So we are not very much concerned with how the total population grows or decreases. So this is artificial. And this is the second equation is the boundary condition at age equal to 0. It means that the number of the newborns, it consists of two parts. One is the part without mutation, and the other part is the portion with mutation. And here I denotes the proportion with how large the portion it is with mutation. And here we have some assumptions on the birth rate and the death rate. For the birth rate, we assume that there's a star, such that for all populations that are older than a star, they will never give birth to a new baby. So, and this is natural for human, right? And the other assumption is that as age goes larger and larger, the death rate will also be larger and larger. And for simplicity, we just assume that it will go to infinity. So people cannot live forever. And here is a numerical experiment with this simple model. Here we take the m to be 0 and choose the birth rate to be this form. So you can see that with this choice, we have the A star to be 3. By the way, here for simplicity, we assume that X does not affect the birth rate. And for the death rate, it has this form. First, the death rate will increase as A increases. And the second term shows that if A is larger than X, the death rate will suddenly becomes large. It means, so the X now here denotes the aggressiveness of the disease. It shows the age beyond which the aggressiveness of the disease increases suddenly. Okay, and initially we choose the population to be concentrated at some x0 in the phenotypical space. And here is the simulation. In the first test, we assume that the population is concentrated at x around 1.5, and let's see how it evolves. You can see that as time goes on, there will be a higher and higher peak. And this peak will push forward to almost 3, okay? It is around 3. And this figure shows how the peak moves. You can also see here, it will goes to 3. So this is the first test. And for the second test, we choose a different initial population that it is concentrated at x equal to 3. So at this time, initially there are some portion with x that is larger than 3. So let's see how it evolves. You can see that now, as time goes on, for x less than 3, it vanishes. But for x larger than 3, it remains almost the same. Okay. So from these two experiments, we can get two conclusions. The first one is that as time goes on with our model, the population with x less than 3 will vanish. So this explains why in nature the inherited disease will not affect people in the reproductive age, okay? And the second conclusion is that it seems that the natural selection has almost no effect for people that is over this reproductive age. As you can see in this figure, for x less than 3, the portion almost unchanged. Okay. So that's why in nature there are still such bad genes. This is just a simple experiment. For us mathematicians, it is a question to understand the concentration appears in this model. Here, I will start from the case without mutation, that is m equal to 0. I rewrite the model here, and I showed that with proper initial data, we will have the concentration as I showed before. So to understand the direct concentration, it seems that this associated spectral problem plays an important role in this process. Here is how this spectral problem is defined. You can see that this spectral problem is similar to the model, except that we removed this time evolution part and changed the right-hand side to be the eigenvalue times the eigenfunction. The Green-Rootman theorem says that for the leading eigenvalue, the eigenvector is strictly positive. Sure, we can normalize it to be 1. It's not a big problem. And for the eigenvalue, there's an equation for it, which is I write it here. This equation is derived from this spectral problem. It is simple. From the first equation, you can derive an expression of the big N by using its boundary value at A equal to 0. And then you substitute this expression into this integral and divide both sides by this boundary value, you will get this equation. Okay. And besides this spectral problem, we also define this dual eigenvalue problem. This dual eigenvalue problem is useful in the analysis of this problem. Okay. So now I will show the theoretical results for the Dirac constriction. If the initial population is well prepared for constriction, to be more specific, we assume that the population initially can be written as the exponential part here times the Q function. Further, we assume that this Q function is bounded below and also above by this eigenfunction big N, and also the exponential part will convert to a Dirac function for some x0. Then it can be proved that the solution has a structure in the long time. That is, nTax will convert to the Dirac function times the big N. And here the constriction point also depends on time. So this is a result by the Samuel Nordman, Benoit Peltham, and Cicely Tang in 2018. Here I will not show the proof of the result, but I will show how we can how this ansatz can be applied to study the problem, to study the asymptotic structure of the solution. Okay, so here it seems that this ansatz is important. So here I use this WKB ansatz, and we hope that this Q epsilon will be fully regular. And then we want to find out the dynamics of this Q and U. So first we substitute this ansatz into the equation for N. We will get this system. So here we divide the first equation into two parts, the blue parts and the red parts. For the blue parts, we combine it together. And so because you can divide the Q epsilon, then you will get an equation for U epsilon only. And for the red part, it is an equation for Q epsilon only. So in this way, you can solve U and Q separately. But if you solve it in this way, the Q epsilon is not fully regular. It's not very good. So what do we do? It seems that the associated eigenvalue problem I defined before is important. That is, I add an eigenvalue here, eigenvalue times the Q epsilon here, and then sum it back. And then we combine the blue term and the together and the red term together, and then solve them separately. Then it will be good. Then the Q epsilon will be good. So here is a summary. This is the equation for the U epsilon, and this is the equation for the Q epsilon. Okay. If you update the U epsilon and Q epsilon in this way, we can prove several good properties. First is that we have the maximum principle for the Q epsilon. That is, if Q0 is initially bounded below and above, then it is bounded below and above for all time. And the second is the conservation law. Here we use the eigenfunction from the dual eigenspectral problem. Okay. And the last one is the limiting equation. That is, we let the epsilon go to 0. Then we should have the maximum value of the U should be 0, and also the Q should be a multiple of the big N, and this coefficient should be independent of time. This is a brief summary of the proof. For the maximum principle, it's simple because we can derive that Q epsilon over the big N satisfies this transport equation. So the maximum principle is just from the comparison principle of a transport equation. And for the conservation law, it is also from direct computation. You can compute the derivative of this quantity should be always 0. And for the limiting equation, we prove for U and Q separately. For the U, the maximum value of U must be 0. It is because we have the uniform boundedness of this integral. That is the integral from 0 to infinity of the exponential of U over epsilon dx should be uniformly bounded by this inequality. because of the uniform boundedness, we must have the maximum value be exactly 0, because if the maximum value of u is positive, then this integral should be infinitely large. And if the maximum value of u is negative, then this integral should go to 0 as epsilon go to 0. Okay, so we must have the maximum value of u be 0. And for the limiting equation for the q, first, the equation for q is exactly the same, the equation for the associated spectral problem. So the q must be a multiple of the eigenfunction, because the dominant eigenvalue is simple. And this and further, we can prove that this coefficient is independent of time because of the conservation law we have proved before. Okay. So in this way, we showed some nice properties of the q and u. So by using, by noticing these nice properties, we are now ready to construct an asymptotic preserving scheme for efficiently capturing the concentration. Our hope is that by using our scheme, the scheme, we can use a mesh in x direction, which is epsilon independent. And so here we can just use the simple finite difference discretization. A uniform structured grid is used, and we use the UKH and QJKH to be the numerical approximations of U epsilon and Q epsilon function. And also we define the discretized eigenvalue problem here. Okay, this is just the simple finite difference discretization. And then we solve the U and Q separately. This is a straightforward discretization of the equation for U and Q. It's worth mentioning that here, for the equation for U, we have a parameter, the big LH. It can be proved that this big LH is uniformly bounded with respect to the epsilon, delta t, and delta x. This is important later in the proof of the AP property, that is a asymptotic preserving property of the scheme. Okay, but I will not show the details here. So now for the scheme, analogous to the continuous case, we have the next properties, that is the maximum principle of the numerical solution, and also the conservation law, and also the asymptotic preserving property of the scheme. Okay. For the last two theorems, the proof is by direct computation. So I will not show it here, but for the first one, I will mention a little bit. In the continuous case, we know that for the maximum principle, it is true because we have a transport equation. But in the discretized case, we cannot prove it in that way. Instead, we can prove it by using the so-called discrete general relative entropy, which is defined here. This is some quantity which will be monotonely decreasing with respect to the time. So here we can choose the h to be any arbitrary convex function. If you take the h to be this form, that is the positive part of u minus gamma k bar square, you can show that initially this h is constantly 0 because we assume that initially the q is bounded above by this part. Okay, and so this quantity is initially 0, so it must be 0 for all time. In this way, we prove the maximum principle. Here are the numerical results for numerical test of our scheme. We compare our scheme with we compute the numerical solution in two ways. The first way is by our scheme, and the second way is to compute it directly from the equation of n. And then we compare it with the exact solution, which is computed with a very, very small mesh size delta x. So the result is here. We compare the integral of n over a. That is, we compare the distribution in the x direction. When the delta x is small, it seems that the numerical solution and also the by our scheme and the numerical solution by directly solving from the n equation are almost identical and they are very close to the exact solution. However, when the delta x is large, the numerical solution, which is the original one with the diamond marks here, they are close to the exact solution, which is denoted by the dashed line. You can see they coincide. But the numerical solution, by directly solving the original equation, has a very large error. Okay, so you can see that our scheme can capture the concentration with a cost mesh. This is a big advantage of our scheme, that the mesh size in the x direction is independent of the epsilon actually. And here is the numerical test for the temporal convergence. Although we did not prove it, but it seems that our scheme works very well considering the temporal convergence. You can see almost the spectral convergence. Now let's move on to the case with mutation. For the case with mutation, there are some differences. In the case without mutation, there is a direct mass, but for the case with mutation, there's no direct mass. But if you let the m go to 0, or you let the epsilon go to 0, this case you will also have a higher and higher peak. That is, it will converge to the direct mass as in this limit. Our aim is to design a scheme that works for all epsilon. But we know that the most difficult part should be the epsilon be close to 0, because for epsilon larger, it seems the solution is smooth, but for epsilon it goes to 0, there will be a peak. Okay. And again, we take the WKP ansatz to study the sympathetic structure of the solution. We assume that the epsilon can be written as the e to power u epsilon over epsilon times the q epsilon. And then we introduce the z to be x minus y over epsilon, and then substitute the equation, substitute the ansatz into the equation. We get the equation here, which is similar as before, except that we have a mutation part. And the mutation part has this form. We can show that by formally taking epsilon go to 0, this part has a limit. This will go to BAX times the Q epsilon over TAX. And this part, it will go to the partial X UI epsilon. So this is what I write here. By formally taking epsilon go to 0, we have a limit for the boundary term here. So compared to the previous case, you can see that you have this eta term. This is something new in the case with mutation. And then for the associated spectral problem, we need to define a spectral problem containing this eta. And then similarly as before, we can derive the equation for the U and the Q. The equation for U is similar as before, but the difference is that now the eigenvalue not only depends on X, but also depends on the eta. And the eta also depends on the partial XU. So it means that the partial TU depends on the partial XU. So this is a Hamilton-Jacobi equation. This is something different as before. It is the right hand side is time dependent now. And for the dynamics of the Q, the equation is similar, and here we have the mutation part. I need to say that with the mutation part, the equation for Q now is coupled in the x direction, so it is more complicated. And besides, formally, by taking the epsilon go to 0, you will see that the equation for Q epsilon will converge to the associated spectral problem. And based on the dynamic equations for U epsilon and Q epsilon, we can do the straightforward finite difference discretization and get this implicit scheme. The scheme may looks very complicated and seems to be difficult to solve because it is implicit. However, it seems that as long as we can solve the eigenvalue at the new time step, then it is easy to solve. So I will say a little bit about how to compute the eigenvalue at the new time step. Here, noticing the equation for the u, and then you can substitute the u h n plus 1 into here and get this equation. And then you can see that the eigenvalues should satisfy this equation, where eta also depends on the eigenvalue. So this is a system for the eigenvalues only. You don't have the u and you don't have the q, you only have the lambda. And then you can just solve this system of equations to get the eigenvalues at the new time step. And in fact, in practice, I can construct a series sequence that converge to these eigenvalues. So it is not difficult to solve this system of equations. Of course, this system can be proved to have a unique solution. Okay. And here is the numerical test of our scheme in the case with mutation. And again, we compare the integral of the density over A, and we compare the distribution in x direction. Here, the dashed line is the exact solution, and the original line with this diamond, the markers are the numerical solution computed by our scheme. And this is the numerical solution computed directly from the original equation. Again, we can see that our scheme can capture, can be very efficient with a Cauchy mesh in the x direction. Okay. Okay, now I have finished the first models, and now I will talk about the second model, that is the populations with heterogeneous mobility and the proliferation rate. This is the joint work with Thomas Lawrence and Benoit Patin. Okay, so let's see first the background. This model can be used to understand the spread of the glioma. Glioma is some dangerous cancer usually found in human brain. Okay, there is a so-called the migration proliferation dichotomy, and because of this migration proliferation dichotomy, it is difficult to treat it because usually the surgery removal of the glioma only targeted at the proliferation part. The migration proliferation dichotomy says that the core of the tumor consists mainly of the proliferative cells, while the border comprises mainly the cells that are more mobile, but less proliferative. Okay. By the way, this kind of phenomenon, that is the core and the border, the individuals, the cells are different, can be found in many problems. One other problem that is similar to this one is the cane toad invasion in Australia. That is, you can find there's an observation that highly mobile individuals are more likely to be found at the border. Okay, which is similar here. So let's see the model. The motivation of the model is to study the spatial spread and the phenotypical evolution of the populations with heterogeneous motility. Here, for simplicity, we consider the 1D in space. Here we use the X to denote the position and T to denote the time, and we introduce another variable Y to denote the phenotypic state. The phenotypic state controls the cell mobility and the proliferation rate. In our model, we use the mu to denote the cell mobility and use the big R to denote the proliferation rate. And also we introduce the population density N and the total population density at a position, which is denoted by rho. Okay. And now here is the model. So the evolution consists of 3 parts. The first part is the red part. It denotes the cell movement. It describes that the cells will move towards the area where the density is lower. So it will move along the direction minus dx0. And here the blue part is the proliferation part. And the last part is the mutation part. Here, I need to say a little bit about the coefficient epsilon here. We put the epsilon square before the mutation to show that it is the slowest process. And we put the epsilon before the cell movement part here to show that it is faster than the mutation part, but it is slower than the proliferation process. Okay. And we put the epsilon before the dTn to for the long term for the long term behavior. And here we have some assumptions of the mobility and the proliferation rates. For the cell mobility, we assume that mu is always positive, so it can only move to the right. And also we assume that the derivative is positive. It means that the larger y is the more mobile the cells are. And for the proliferation rate, we assume the contrary. That is, if the larger y is, the smaller r is. That is, for cells that are more mobile, they are less proliferative. This is from our assumptions on the model. Okay. And now with our model, we do some numerical tests. I will first show a test with bounded y, because here we assume that the r should be, we should assume that r or big Y should be 0. So here, if we take the r or y to be 1 minus y square, then the big Y should be 1. It is bounded so the y is bounded from 0 to 1. And in this case, you can see the plots of the normalized density n, and also the plots of the density rho. You can see that at the time t equal to 4, t equal to 6, and t equal to 8, you get almost the same structure at the front. So we get the traveling front solution. Okay. And here is another test. Here we choose a different r, which is 1 minus y over 1 plus y. So in this case, the big Y is unbounded because y can go to infinity. If y go to infinity, the r of y go to 0. Here I choose y to be 20, but if you want to compute it for a long time, you need to choose a larger big Y. So it is an unbounded case. In this case, we observe a completely different phenomena. You can see that we still have front, but the front, the structure of the front is changing with respect to the time. As time goes on, the front is stretching and stretching. So this is some interesting phenomenon from the numerical. So how do we understand it? Here I will show a formal asymptotic analysis to study this problem. Again, we take the WKB and that we assume the n epsilon to be the e to power u epsilon over epsilon, and then we substitute this and that into the equation for n. We get the equation for the u here. Formally, if we let the epsilon go to 0, we throw away this term, and this term we get the equation for the limiting equation u. And besides, another quantity we are interested in is the dominant phenotypic trait, which is denoted by the y bar. So later I will show something about the y bar and the u. First, we have some constraints on the u and y bar. First, for the constraint on the u, we should have that the maximum value of u should be exactly 0. This is because of this and that. If the maximum value of u is less than 0, we should have this one will go to 0 everywhere. And if the maximum value of u is larger than 0, then this term will go to infinity. So the only possibility is that the maximum value of u should be 0, which from here we also get the partial derivatives should also be 0. And for the y bar, because we have if we evaluate this equation at y equal to y bar, then this partial derivative should be 0. So the only thing left is the r. So we should have the R of y bar and the rho should be 0. So this is a constraint on the y bar. Next, we can derive a transport equation for the y bar. We differentiate the equation for the u here, and evaluating at y bar, we get this equation. It's worth noting that the last term disappears because the partial derivative at y bar is 0. And then from the constraint on u, that u at y bar should be 0, then we get some expressions of this second order derivatives, and then we substitute these expressions into the equation here. We get the transport equation of the y bar, which is written here. Next, we show the traveling wave analysis. That is, we consider the y bar is bounded case. For the traveling wave, we take the ansatz that is, we take z equal to x minus ct, so the traveling speed is c. And then we assume that the density and the u and the y bar should all have this kind of form. And then then the equation for u, it changes to be this one. We do not have the partial t term, but instead we have the c times this term. And also for the y bar, for the transport equation of the y bar, we have this equation. And the first result we can get is that for the traveling wave, we can prove that the traveling front is monotonely decreasing. This can be proved in this way. That is, first from the transport equation, we have this one, and also from the R of y bar rho equal to 0 and differentiated with respect to z, we get this one. And from this equation, we can have an expression for the rho prime, and then we substitute the expression into the first equation. We get the y bar prime should have this form. And now you can check the signs of each term. For the big R, you know that the partial derivative is over y is negative, so this term we have a minus sign here, so it is positive. So this term should be positive. And for this one, the denominator is minus partial rho of R, and also by the assumptions on the R, you should have it is positive, and also here it is square. It is positive, so this term is positive. And for this term, at y equal to y bar, you know that u takes the maximum value at this point. So the second order derivative should be negative. So here you have a minus, and this term should also be positive. So in this way, you showed that the y bar prime is positive. And from this R of y bar rho is 0, then you can get that the rho prime should be negative. So in this way, you showed the traveling front is a monotone decreasing. Okay. And another result we can have is the minimal wave speed. That is, if we consider the R takes this special form, then there's a minimal wave speed C star, which has this form. I have a remark about this minimal speed. That is, if you have the as y big Y go to infinity, if you have this one go to infinity, then the minimal wave speed should also go to infinity. It means that we do not have a traveling wave speed. This is consistent with our second numerical experiment where the big Y is unbounded. Okay. For the proof, so here we have the expression of the y bar we have derived before to prove the monotonicity. And here we notice the special choice of the big R, and then we can substitute the dyr and the dρ r into here. We get the this equation. You can see that you can view this equation as a quadratic equation of the y bar prime. Here you have the first order. Here's something independent of the y bar prime, and here you have the quadratic term of the y bar prime. So we know before that the y bar prime has a positive real value, so real solution. So for this quadratic equation to have a solution, we must have some constraint on the coefficients, and from there we can get the lower bound. Okay. Lastly, I will briefly say how to do the numerical computation, that is the numerical scheme. Because because in the simulation there is a stiff traveling front, so an implicit scheme is needed. And besides, the time-relating method can be applied to further simplify the problem. That is, we solve the advection part and the growth part separately. And here we use the uniformly structured grids. And here we just define some notations for the numerical approximation. And for the advection part, in each cell, we can just use the finite volume method here. At the boundary, we just use the upwind numerical flux at the boundary. And then it can be shown that this simple, straightforward scheme has the nice properties. That is, assuming the solvability of the scheme, then we should have that the solution are non-negative, and also we have the maximum principle for the density, and we can also show that the density should preserve the monotone, should be monotone preserving. Okay, so all these are designed properties from our formal asymptotic analysis. And for the growth part, we do not solve the equation for n. Instead, it seems that if we take n equals e to power u over epsilon and solve the equation for u, it is simpler. And it can be shown that if you solve it in this way, the scheme admits a unique solution, and it is positive. And also we have the maximum principle for the density, and also the monotone preserving property for the density. So combined these two schemes, we can see that our scheme will be preserving the structures of the solutions. Okay, so this is the end of my talk. Thank you all for your attention.